So, while I was bored doing homework, I decided I should just start drawing. And while I was drawing, I decided to draw squares, because squares are nice shapes. So, I started drawing squares, like the one that is right here, and I decided to just start drawing some lines on the inside of them. When we were drawing our squares, we decided to put the lines connecting the inside of the sides. So we started with the first point on the first side and connected that to the second point on the second side, and then the second point on the first side to the third on the second side, and so on and so forth, until we connected all the points on the first side to all the points on the second side. Once we finished with the first side, then we decided to go from the next side, so side 2 to side 3, and we did the same process where we connected the first dot to the second dot, and so on and so forth, and we did that until we had finished with the entire square. After making multiple different squares with different lines on the inside, we noticed that the area made from the inside wasn't always the same, and we wanted to explore the pattern. Since each of these squares had different shapes on the inside, it was pretty hard to find the area. So what we did was we inscribed a circle, the largest possible one, on the inside and took the area of that, so it'd be easier to find how it compared to the area of other squares that we made. After drawing the circles on the inside, it was still hard to find the area. So we made some rules so that way we could find the area on the inside easier, and so we could develop patterns with these areas. The first rule that we put in place after we drew the shape was we have to have evenly spaced points on each side. For this shape, we're having size 1, so there's only one point on each side. With these points, then we have to move a specific amount each time, and that is one of our other rules. This one, we're moving one point each time, so it makes a shape like this. This time we're going to use size 1 and move 2 to show what happens when we end at a spot that is already touching another spot, and there's still available spots open. When this happens, we start at the next spot and continue until there are no available points. We kept using size 1, but we kept moving one more point each time to see what if there would be a pattern in what we did. So for this one, we're doing size 1 again, but we're moving 3. And it happened to look exactly like the size 1 move 1. And we kept doing this until we moved the total amount of points that there are. So for this last one, it is size 1 move 4, which ends up with just a blank square. These ones we use the exact same pattern, except for this is for size 2. And with these ones, this is size 3, where we go from moving 1 to moving 9. This one is size 4, which goes from moving 1 to moving 16. After doing all of this with squares, we thought, what happens if we try this with other shapes, like triangles, squares, and pentagons? For this, we had to add another rule to our list, which was only using regular shapes. Since we're using regular shapes, we have to talk about a one-sided shape and a two-sided shape, but since they don't have area inside of them, we can't do much with them. As we created more and more examples, we started to notice a pattern. It was similar to Pascal's triangle or combinations. There's many repeats in numbers, as 5 choose 1 is the same as 5 choose 4, where the first one in each pattern we made is the same as the second to last, if we don't include 0 movement. But the very center one always didn't have a counterpart to it, and this happened to always have the lowest area on the inside, which we noticed. With looking at all these examples, we started measuring the inside area of the inscribed circle, and we found that the largest area is always when we either move 0 or we move the maximum amount we could, and the smallest area was when we moved the half amount we could. And every number in between kept getting closer and closer to 0 as we got closer and closer to the half amount of total moves we can. To define what we used as the area of the inside, we would inscribe the largest possible circle and take its area, so that way it was easy to do it for all shapes.
To illustrate the conclusion and results, these pictures that have the yellow corners show that as you move the minimum amount of points, the area is the greatest as shown in this diagram. Also, if you move the maximum number of points, the same diagram will appear.
This is what a triangle looked like when we approached infinite points and infinite moves on each side. These were some of the results when we used a triangle whose side length were 6 inches. So when we did 1.5 the number of total points, like how much we moved, we always got as close to 0 as we could. With without actually getting to 0. And we did the minimum number of points. We got 7/8 of an inch, which is the largest possible inscribed circle we can make with a triangle, which is similar to the result of the square, where the middle number of movements we had gave us as close to 0 as possible, but with the square it was actually 0, and with the triangle was approaching. And when we did the lowest number of movements, we got the largest possible inscribed area. This is what the pentagon looked like when we approached infinite points on each side and infinite moves for each point. These were the results we had when we added more and more points to the side of a pentagon. And this was the area that we found on the inside when we would draw about the half amount of total number of moves. And as we added more and more, we found that the answer got closer and closer to 0. This is an example of what the results show. A pentagon with multiple dashes where each of the lines is about half as many moves as we can possibly have. As you can see, the center looks like it has 0 area when it actually has a small amount. These results are not only for pentagons, but all odd-sided shapes, where the closer you have to half the max number of moves, the closer you are to 0 area on the inside. When using a pentagon whose side length is 4¼ inches, these were the results we had when we kept adding more and more dashes to each side and checking the inscribed area, with only moving enough to make a pentagon for each side. When doing this, we found the area led up to 1.98, but never got exactly 1.98 inches. This shows that when moving the lowest amount of points, we get the highest amount of area. To generalize our findings, when we moved the minimum number of times we could, we always got the largest area for the shape. And when we moved half the number of times, we would always get the minimum area. For even-sided shapes, this area would be 0, and for odd-sided shapes, this area would approach 0 but never become 0.